Hello everyone and welcome to my presentation. My name is Ege Korkan and today I will be presenting to you our paper called Web of Things System Description for Representation of Mashups. If you'd like to follow up on this talk, you can join the session on August 31st at 10:40 a.m. As we all know, the amount of the IoT devices, whether in personal, smart home, or industrial contexts, is increasing. So we are very familiar with such devices in the smart home context, such as lights, speakers, smart locks, and so on. However, with the number of devices, also the number of platforms, middlewares, and frameworks is increasing. And the most important question we have is how can we now use such devices that are connected to the internet to compose useful systems? We will refer to these systems as mashups in this presentation. So we would call them IoT mashups. Once we want to do such mashups over the internet, so meaning that when the devices are in different local networks, so for example, connecting such a robot with a sensor, we see that it is actually not so straightforward. And even though it is possible, it requires a lot of manual implementation effort. And generally, we say that they are not very interoperable. And this is actually a big blocker for the Internet of Things, since it doesn't allow us to compose big systems that the internet is promising. So when we talk about Internet of Things, we should actually not forget the word internet in it. And actually, when we think of the internet, we generally also think of the web. And the web actually doesn't have such an interoperability problem. We are able to compose systems very easily by using different services. So for example, in a hotel booking website, we could very easily use map information from one service, weather information, maybe even live from another one, and we could actually offload the payment to another service. And these have been possible, and they are called the web mashups, and they are everywhere these days, even if we don't see them on the user interfaces. And with this, we come to the word Web of Things. So how can we have such kind of systems in the Internet of Things by using technologies found in the web? So the Web of Things is a term coined around 2008, and it allows us to interact and model devices that are connected to the internet in a way that is analogous to interacting with web APIs. So Web of Things says that we could imagine each device and its capabilities as different resources. These resources could be sensors or actuators. And the Web of Things is currently being standardized by the W3C Web of Things working group. This working group has different types of deliverables, and the architecture specification and the thing description are published as of April 2020. And the scripting API, which is in Works, is very important for this paper, and that's why underlined. In the working group, there are different companies of different domains. So here we can see industrial companies or industrial device manufacturers, cloud providers, telecommunication providers, the device manufacturers for smart home. And then recently there are even more companies joining and are active. As you can see here, where there's also a DNS provider, for example. And if you look to their webpage, you will see that there are actually many more other companies who are contributing to the standardization efforts. So let's start with the Web of Things architecture. And basically, the Web of Things architecture describes different use cases for Web of Things, thus for Internet of Things. and it coins the terms interaction affordances and operations. So interaction affordances are quite straightforward. We have properties, action, and events. And these all correspond to different types of capabilities of the device that could be used over the network. So let's see some more details. So in the case of properties, for example, we with properties we mean reading sensor values or changing configuration parameters of devices. So these values can be read or observed or written. And also what we see here is that we have things. So this is what provides the capability, and we annotate every other entity that interacts with this thing as a consumer. So this could be another device, it could be a browser, it could be a script running in your computer, anything basically. With actions, we annotate capabilities of devices that actually change the physical state of the device, such as rotating a ventilator, turning on a light, moving a robot arm, and so on. And lastly, the events are self-explanatory, is what the consumer can subscribe to, and the device notifies the consumer when the event happens. So this could be like a button press, but it could also be event streams like position of the robot. Then, most importantly for this paper is the thing description standard. So here we see an example thing description, a rather simple one. And on the left-hand side, we see some metadata such as security information. And on the right-hand side is the interaction affordances. So as you can see, 3D thing description is a document format that is machine and human readable. So in this case, this is a JSON LD document. And as you can see, it allows us to describe, for example, the data structures of a property or action. And here also we can see that with combining with a base value, we could also describe the exact endpoint of a device. So this is to say that these are device specific and not general API descriptions. And similarly, we see the actions and events. And very importantly, here we see that the event is using another protocol, so in this case, CoAP. And this is to show that with thing description, we can combine different protocols. So here we can also have MQTT or Modbus for industrial cases. And this is one of the powerful aspects of it, since this abstraction provided by the thing description hides the protocols, and we can just talk regarding reading properties, invoking actions, and subscribing to events. In this context, the mashups, so which is the focus of this work, is basically any system that is composed of multiple things. So we could imagine a case where we have environmental sensors that could be used by a mashup to calculate the rain probability, and then we could reuse this rain probability by an outsider consumer, by an outside consumer, to, for example, control an activated window. So if there's a rain probability that is high, we could close the window. So currently, these mashups are represented mostly via code or tool-specific methods, such as with Node-RED. However, as you can see, so here is what we see as a part of the scripting API. So the scripting API allows us to program in a way that is abstract from the protocol. So the read property, for example, here would map to the concrete protocol request. However, even though the scripting API helps a lot regarding writing the mashups, these mashups are not very interoperable between different platforms. So when we write such a code, this code won't be executable by another environment. So in this case, this is a JavaScript code. It will not work in a Python environment, of course. This code is generally manually written, so pretty programmed. The interaction affordances, so what we are exposing to the outside, so the stream probability, it is not straightforward to do it, and it limits the mashups from being reusable. As with any code, so in this case, it might be a simple case. The code can get complicated, and it will be then difficult to understand the actual logic inside the mashup. Thus, we say that a new representation format is required if we want to increase the usability of these mashups. And thus, we're proposing a mashup management approach. We first start with a sequence diagram representation of the mashups. So in this sequence diagram, we see what messages are sent between different devices. Then we provide what we call a Web of Things system description. This is an extension to the thing description, which is machine and human readable and describes the mashup. And very importantly, the conversion, which you see in the middle, is what allows us to represent the same mashup in two ways and automatically convert between them with a sound equality that we will show. And then from the system description, we are able to generate code that would be deployed onto a mashup controller. So this mashup controller would then control the different things. Then, like we said, we could then create the interaction affordances for other consumers, so that these consumers can use the mashup or monitor it. So first, with the sequence diagrams, so we are proposing a subset of the UML sequence diagrams standard, and which is very frequently used in the industry for specifying how the messages and their orders should be between different agents. The UML sequence diagrams are visual, but we could actually use tools like PlantUML, which have a textual representation. And in order to constrain this, for our case, to describe mashups, we have defined a grammar. And this grammar also allows us to validate such descriptions. And from this, we can very easily, by any PlantUML renderer, we could also generate a visual representation which allows a human to confirm what the mashup should be and whether it conforms to his or her expectations. So here we see the most of the elements that we are proposing for sequence diagrams that are specific for Web of Things mashups. Here on the top, we see the mashup controller and the involved things. So the mashup controller interacts with these things. Then we see the type and name. So here, what is triggering the mashup. So this is then a function. And then most importantly, here inside it, we see the actual interaction sequence that can have logic. So things that could be running in parallel and that actually sends the requests to the physical devices. And lastly, we can also see that we can set variables to different values such that we could reuse them later on. So these would be then internal variables. Then here is the system description that we are proposing. So system description is, like I mentioned, is an extension to the thing description, and we extend it by using the keywords such as things, which mean the different things involved in the mashup, the path, which contains the application logic, then like shown in the sequence diagram, the internal logic and data, and also, of course, all of these can have different keywords for their child elements. Very important is that the system description, like thing description, is a JSON LD file, and we also provide contexts and an ontology such that it could be linked to different vocabularies and could be then used in other places in the web. Here we see an example, and also we provide a JSON schema definition such that this could be easily validated. And as you can see, here we have the function, so what starts the mashup. And then here we see the actual interaction sequence where we receive a value from an event and then act on it by sending it to a device. And here, as you can see, we generally talk about these atomic mashups where we first try to receive a value that could be then used, very similar to how control loops work. Then, as I said, it is very important that these are interchangeable, and to do so, we are providing an equality proof, and this ensures that we could convert both into each other and then use the advantages of both formats, meaning that sequence diagram, a visual format for humans to understand how a mashup looks like, and on the other hand, a system description that could be then exposed for other devices, could be read by machines much easier, and could be linked to other documents. So for our proof of equality, we first start with by stating what is the formalisms to represent a Web of Things mashup. So in a way, we could think a mashup as a sequence of interactions with some application logic. We then conclude with the formalisms on what it should be for a sequence diagram and for a system description. And later on, we show by comparing their equality such that in the end, we can say that the sequence diagram and system descriptions are equal and can be used interchangeably without losing any data. So more details on the proof and all these details could be also found in the paper with much more thorough explanations. In the end, we could say that we have two algorithms. So first one is for the conversion. So for any type of input, whether it's a system description or a sequence diagram, we have an internal representation that we convert to, and from this internal representation, we generate the output. So output, again, is the opposite of the input. And then for the code generation, we start with the system description, and again, we parse it for an internal representation. And from this, the code can be generated, which could be directly used to communicate with the devices. Our implementation is based on TypeScript and Node.js, and it is using the Node.wat implementation, which is the reference implementation for the scripting API. And it is available in this link in our GitHub page. The related work for this paper could be summarized. First, we note the Web of Things based asset description, which is very similar to thing descriptions, but tries to extend it by linking to different things. However, it lacks any way of linking the logic between the devices. Then there is the Whatify, which is also a web page, and in this case, it makes it easier to find the devices that we would need and how we would implement them. However, how to combine such devices and the logic between them is also missing. And lastly, there is the What's Store. That is a software which allows us to link different things in an environment and also to deploy the code for them. However, the code doesn't have any formalisms to show it as like we shown with as a system description like format or a visual format like the sequence diagrams. However, it makes it much easier to develop Web Things applications. Then for our paper, we have evaluated in 3 case studies. In our setup, we had the physical things, and we connected them over the local network where the mashup controller is on a laptop. And we have always evaluated it by creating a sequence diagram by hand, converting it to a system description and reconverting it back to a sequence diagram and check their equality. And then after this, we have deployed the code that is generated from the system descriptions and run it to see whether the logic that we are expecting is actually happening by observing the physical devices. For the first case study on the top right, we start with a very simple one where we have a button that would turn on an LED strip with a certain time. In the second case study, we took an example from the second W3C Web of Things workshop, where there is a smart home scenario, and we have basically took a case where the goal is to turn on or off the lights when a person leaves or enters their home. And what is particular for this case is that the mashup is then re-exposed as another interaction affordance to the outside, and we can use a Mozilla Web Things gateway to control the mashup. So as you can see on the first case, we don't expose the interaction affordance to the outside since we don't have to, and in the second case we can do it, and it is also to show that we can use different software solutions to manage the mashup. And this means that what we are proposing is not a strict framework, but it could be very easily integrated into other platforms. And the last case study, we have increased the amount of devices considerably, and the logic that is needed to accomplish it. And here we see that we need to sort different cubes that are on a conveyor belt and that needs to be stopped when they are on a infrared sensor, and then a robot would pick and sort them based on their color. And here again, we didn't expose the mashup to the outside, and as you can see, the logic that would be needed for such a mashup is then considerably more. Then we have looked at different metrics from these case studies. First of all, the mashups that we generated from the system description were perfectly doing the logic that they were intended to. Secondly, the conversion, so back and forth, was successful, meaning that our equality proof holds true. And then we also have some other metrics where we could also then see that, of course, with the increase of application logic elements in the third case study, the amount of lines of code also increases, but also the number of devices has a contribution to this, where we can see that in the second case study, even though there is not a lot of application logic elements, the generated code is rather similar to the first case study, which has more application logic element but less number of devices. So to conclude, in this paper we provide a sequence diagram based representation to give an insight to Web of Things mashups. We show that we could have a system description that represents the mashup in a way that is similar to the thing description. And importantly, we prove that both are interchangeable. And from this, we could generate the code that significantly reduces the manual effort, and that we could very easily create the interaction affordances for other consumers to interact with the mashup. As we have seen, we have evaluated with 3 case studies, and in overall, we can say that our contributions improve the Web of Things mashup management significantly and allows us to have a more systematic way of thinking about the mashups. Here are some references that were used for this presentation, but the references relevant for the paper are in the paper. Yes, and thank you very much. Here is my contact information. You can use any of the methods you see here, and I'm hoping to meet with you in the live session of 31st of August at 10:40 a.m. Thank you and bye.